just a few minutes before having lunch. So I will... Plenty of time? Okay. 30 minutes. And then you will have lunch, so it's good. So my name is Eric Grivel. I'm coming from Bordeaux. It's not very far from here. Bordeaux is a very nice place also where there are nice vineyards. But of course, Toulouse is also a very nice city. Today I'm not going to speak about geography or history, but I'm going to discuss about the properties of the cross-entropy or photoregressive moving average processes, because I'm involved in the field of signal processing with a lot of data, time series. And so usually we have to use this type of model in order to, of course, extract information. So, of course, cross-entropy is widely used in our community in the field of information theory, of course, in the field of deep learning. But also, when dealing with time series, it's always interesting to compare time series by using some tools, it can be also of interest within a single time series to identify some statistical change, what we call in fact change detection. It has many applications, especially in the field of biomedical applications, in the field of speech processing, in the field of mobile communication system or radar processing also. It is true that, as you know, there are a wide range of models that can be used when having data recorded by sensors. And we can, depending on the properties of the signal, we are going to use a specific model. This can be if the spectrum is discrete, a sum of sinusoids. And when it is rather the spectrum is continuous and with a short memory, we are going to focus our attention on autoregressive and moving average model. When it is long memory processes, it is rather RFIMA processes, and when it is rather nonlinear, of course, we are going to focus our attention on Volterra models or variance. Today, our purpose will be to, compare Gaussian ARMA processes. ARMA processes are used in signal processing and widely, especially in speech processing, biomedical application. And today, the idea is to extract and to analyze the properties of the cross-entropy between the probability density function of consecutive samples of two ARMA processes. The idea is to see how evolve the cross-entropy when CAD varies. So just to recall you some interesting results we are going to use concerning ARMA processes. So an ARMA process, as you know, is defined as the following, by using the following equation. That means that the kth sample can be expressed from the pth previous ones as a linear combination. And then there is a linear combination of samples that in fact corresponds to a Gaussian white noise. So it can be seen from a signal processing point of view as the filtering, the linear filtering of a white noise. This is like an excitation, a driving process that then has been modified by a filtering. And this filtering is interesting because, of course, by taking the Z transform, you can have the transfer function that can be characterized by the ARMA parameters, but also by the poles and the zeros of the transfer function. And we can easily express the power spectral density from the variance of the driving process, that means sigma u square, but also the poles and the zeros of the transfer function. it is known as a wide-stance stationary short memory process. Concerning the ARMA parameters, you know that we can estimate them by using, for instance, the Yule-Walker equations for the autoregressive part. We can also use some online methods based on some adaptive filters such as the LMS or the RLS. Concerning the correlation matrix of finite size K, it should be noted that it belongs to the Wiener class Toeplitz matrices. It is non-singular, even if the PSD has some zero at some is equal to 0 at some frequencies. This point is interesting and important. It just means that the correlation matrix is invertible, and so it is, of course, of importance. As a matter of fact, different ARMA processes can be characterized by the same correlation matrix, and so the same PSD. The only difference between one ARMA process and another one is the fact that this is the position of the zeros that can change. And if we take an example of a first-order moving average process, it is in fact the case when you have all the AR parameters that are equal to 0, and there is just B1 which is equal to the 0, to the opposite of the 0. Then in fact we can slightly modify the transfer function, and we can express it as the product of three terms. So the transfer function here is written by a specific zeros that can be outside the unit circle, and we can express it differently by using another transfer function of an ARMA process whose zeros in this case is inside the unit circle. Here you have something that looks like a Blash product, and here this is just a constant. As a conclusion, we have here something that is stable as a filter. And so what is interesting is the fact that when you have one correlation matrix, you can always find what we call a minimum phase ARMA process. That means an ARMA process whose transfer function has all its zeros inside the unit circle in the Z-plane. The last point is the fact that usually when you can define a transfer function, you can also look at its inverse filter, and in this case we can here exploit the fact that we can consider the minimum phase filter, and the inverse is defined as follows. By taking into account all these properties concerning Gaussian ARMA processes, let us now look at some information concerning the entropy, but also the Kullback-Leibler divergence between the PDF of ARMA processes and the cross-entropy. So here we are going to recall the definition of the entropy associated to the PDF of K successive sample of an ARMA processes. Here, of course, this is the definition for the Kullback-Leibler, and the cross-entropy can be expressed from the entropy and the Kullback-Leibler. As we are working in the Gaussian case, we can exploit the analytic expression of the PDF of the Gaussian processes and substitute in the previous definition in order to obtain the expression of the entropy and the Kullback-Leibler. And in this case, you can see that for the entropy, we have in fact three terms. And concerning the Kullback-Leibler, there are once again various terms the first term here are rather related to the covariance matrices, whereas the last term is can be expressed by the mean. In fact, concerning ARMA process, usually the process are zero mean. That means that these terms could be equal to zero, but we can also have some ARMA process that can be then with a mean that is not equal to zero when we had a mean. And so then we can extract the cross-entropy. And now the idea is to look at this expression and to try to find to analyze the influence of each term concerning the cross-entropy. For this reason, we are going to compute the increment of the cross-entropy. That means that we are going to make the difference between the cross-entropy when we consider covariates and the cross-entropy when we consider k+1 variates. So by computing the difference, we will obtain the increment, and this increment is in fact just the sum of three terms. So the first one, it is quite simple. This is the logarithm of 2 pi, so it is not of real interest. What is more interesting is the second term, which is the difference of two traces. The first trace involves the covariance matrix of the first ARMA processes that is pre-multiplied by the covariance matrix of the second process, and their sizes are all equal to k+1. It is exactly the same thing for this term, except the fact that the covariance matrices are of size k. The last term is the logarithm of the determinant of the covariance matrix. Here, the determinant is this is the determinant of the covariance matrix of size k+1, whereas here you have the determinant of the covariance matrix of size k. So looking at this, it is true that we may wonder what the type of information we can extract from this increment. For this reason, we are going to take advantage of some results, especially in the field of information theory. When we analyze some divergences, we look at the way the divergence evolves when k increases, in order to obtain the divergence rate. Here we are going to do exactly the same thing. That means that we are going to analyze how this increment evolves when k increases. So we are going, in fact, to do an asymptotic analysis of this increment when dealing with Gaussian ARMA processes. So let us first, here is the increment, and now the idea is to look at the limit of this difference when k tends to plus infinity, and then we will look at these terms. So this term can be seen as by taking advantage, for instance, by using the eigenvalue decomposition of the covariance matrix, we can show that this difference between the two traces can be seen as the power of the first process filtered by the inverse filter corresponding to the second process. That means that we try to find a physical interpretation of this difference when k tends to infinity, when increases. And so what is interesting here is the fact that we can have here a physical interpretation of this part, which is just taking the first ARMA process and then using filtering it by the inverse filter associated to the second one. And then we just compute the power. So it is the first part. Let us now look at the logarithm. Concerning the logarithm of the determinant, the idea was to try also to analyze it and probably to find an analytic expression. For this reason, we are first going to introduce the normalized covariance matrix. That means that we just divide the covariance matrix by the correlation function for lag equal to 0. Then, of course, we can re-express the ratio of the determinant, and we obtain this ratio, which that means that we can express it from the power of the first process, and then there is the ratio between the determinant of the normalized covariance matrices. At this step, the idea is to take advantage of some results from the determinant of Toeplitz matrix and more particularly Toeplitz matrix of ARMA processes. And in fact, this determinant can be expressed from the partial correlation coefficient. I don't know whether you are familiar with the partial correlation coefficient, but they correspond to the contrary of the reflection coefficient that are used when you, for instance, in autoregressive process, you have the AR parameters. The AR parameters can be estimated from the U-Walker equation. As an alternative, you can estimate the reflection coefficient by using the Durbin-Levinson algorithm. And in fact, the partial correlation coefficient corresponds to the opposite. And it is interesting to see that we have the determinant that can be expressed from the PSCF as follows. That means that we can have an analytic expression of this ratio that can be expressed from the PSCF. Now the question is to say, okay, what happens when K increases? As a matter of fact, we can take advantage of the results from the Durbin-Levinson algorithm. When we look at the Durbin-Levinson algorithm, we can see that the variance of the driving process, we can have, in fact, a way to estimate it in an iterative way. And so, looking at the limit, we can see that this limit is, in fact, equal to the variance of the driving process associated to the minimum phase ARMA process corresponding to the second process. So in fact, this limit just corresponds to the variance of the driving process associated to the minimum phase of the second, the minimum phase filter of the second ARMA processes. As a consequence, we are able now to look at the limit of this increment, and we can show that this limit has this specific expression. That means that this is here the power of the first process that is filtered by the inverse filter of the second process, and this term is in fact related to the variance of the driving process of the second ARMA process. What does it mean? It means that if you have here, when you look at this power, and if you see that there is 1 0 on the unit circle that is not shared with by the first filter, this power will go to infinity because the filter is no longer stable. That means that in this case the increment will be infinite, and so that just means that when you will try to compute this asymptotic increment, you will get something that is infinite. So what is interesting in this part is the fact that it also does not depend on k. So you can use it directly to characterize the cross-entropy between the two ARMA processes. So some illustration. We just compare two moving average processes characterized by different zeros. So here you have the different values of the zeros, and you can see that the asymptotic increment evolve when the zero of the second process change. Here we have also analyzed the way the asymptotic increment evolves, and you can see that it converges to the asymptotic increment we defined in the previous section. So we can use this asymptotic increment then for the comparison between ARMA process. It is exactly the same thing for AR process, except the fact that here you can see that when using ARMA process, just autoregressive process, there is not a transient behavior concerning the increment. You directly converge to the asymptotic increment. As a conclusion, our purpose here was to analyze the cross-entropy between the probability density function of k consecutive value of two ARMA processes. It was motivated by the fact that in our field we have to compare some data from different speakers, from biomedical signals, and the idea was to use the asymptotic increment to compare this data. This work is within a more general work when we try, in fact, to give some physical interpretation of this type of criterion. This is done with Kullback-Leibler divergence, with Jeffreys divergence, with Rényi divergence. And each time we try to see, in fact, we try to give a physical interpretation to this type of increment. Thank you for your attention.